Welcome to the fourth lecture from chapter number 4. In this lecture, we'll study doped silicon layers, and we are studying fabrication of CMOS ICs in this chapter number 4. Right. So doped silicon layer is a silicon layer doped with either N-type or P-type impurity. And we'll see how in modern CMOS this doping is carried out. So a silicon wafer is the starting point, which is actually doped. It's a round circular disc, and it is round so that certain manufacturing or fabrication processes can be carried out easily. Right. So a doped silicon is actually a patterned N or P-type material, a P-type material or an N-type material, and it is in the form of this or this or this or this, something like this. All angles are of 90 degrees. So our drawing may be poor, but all angles are of 90 degrees. And the materials are, at the same time, materials are either N-type or P-type material. And we already know that an N-type material is obtained by adding a pentavalent impurity such as antimony, and a P-type material can be obtained by adding a trivalent impurity, for example, boron, right? So doping is the process of introducing either donor is, for example, antimony, or acceptor. Acceptor is a trivalent impurity, donor is a pentavalent impurity, right? So the technique that we use for modern VLSI design is ion implantation. It's a modern technology used for doping. How is it? How is a silicon wafer doped of either P-type or N-type impurity, right? So it's a given wafer. We want it to be doped or a part of it to be doped using either a P-type or N-type impurity. So the impurity ions, these are impurity ions. Impurity ions are heated in a chamber such so that until they achieve an energy around 100 to 200 kilo electron volts, right? So they are heated up in a chamber and such that they convert into ions, and then they are accelerated in an accelerator, and then they are passed through a magnetic mass separator that separates N-type or P-type impurity ions, and then with using this pointing gun, a part of a wafer or full wafer is doped, right? So this operation is carried out when these ions have this much energy, around 100 to 200 kilo electron volts. So they're heated up, they're well heated up. So particle diffusion, when they enter into this wafer having a very small thickness, not all ions, they stop at the same distance. This is the cross section of the silicon wafer. This wafer is actually a cross section of this wafer. We cut it with a knife and we see that some impurity ions, they land here just in the beginning. Some penetrate deep into the silicon wafer, some stay in the middle. It depends, because not all impurity ions are having the same energy. So the stopping distance, the distance at which they stop, it also differs. Some stop here, some stop in the middle, some penetrate very, very deep in the silicon wafer. So these bombarded impurity ions stop in silicon wafer at random depths. So some stop earlier, some penetrate more than others. So if this x represents a variable that represents the depth of a variable that represents the depth of the silicon wafer. It has a range from 0 maybe to a capital X, which actually represents the maximum possible depth. So X is a variable having a number between 0 to capital X. If capital X is the maximum depth, right? So X is a variable that represents a number between 0 to capital X. So wafer then is annealed or heated to get impurity ions in their proper locations. After they are bombarded, they are then annealed. After these two steps, the distribution of impurity ions in the wafer can be represented with a Gaussian distribution. Gaussian distribution is a probability distribution that we have studied in probability and statistics course. It's NP times e to the minus 1 over 2 x minus rp over del rp squared, and we already know that this from elementary courses, we know that this number is mu, the mean x minus mu squared over sigma, or x minus mu squared over sigma squared, and number in the denominator is sigma squared, its variance. So this is actually rp is the mean, and this del rp is the variance of this Gaussian distribution used to model the presence of ions in the depth, along the depth of the silicon wafer. So rp, that is the mu or mean, is also called projected range, and the standard deviation, which is the square root of this variance, is also called straggle. Right. And total ions can be represented as by computing integrated this n of x integrated from 0 to the maximum depth, capital X, this much. So you can, if you integrate it using in this range of x, we will count all number of impurity ions. That's obvious. How is the thing that is missing here in this lecture is one thing that I missed, is the plot. How is this plotted? Versus x, this distribution is plotted like this. So on x-axis we have this x variable, and on y-axis we have this n ion of x. And we know from the probability and statistics course that this line is the mean. This vertical line intersects this horizontal axis at a point that is equal to the mu, that is the mean. So this is the mean. This means the majority of the atoms will be stopping here. The probability that a given ion stops at this much distance when x is equal to rp is the max, right? And this is the standard deviation del rp. Del rp is large, this width of the curve is large. So del rp is a quantity that is directly proportional to the width of this curve, whereas rp is the point on x that has the maximum probability. So it is somewhere in the middle. So if we somehow locate it graphically, rp x is equal to rp would be somewhere around here. So majority of the ions, impurity ions that are bombarded using ion implantation technique will be found here. And as we move away from this vertical line, number of impurity ions would decrease. There'll be very small number of ions just at the border, and very small number of ions when small x is equal to capital X. Deep, very small number of ions will be in the beginning and in the end. Majority of the ions will be in the middle, and the distribution along X would look like this. Right, that's all for today's lecture. In the next lecture, we will keep on studying more IC fabrication techniques. Thank you.